afternoon and good night. Welcome to LBN Low Budget News, where we present to you quality news on the cheap budget. I am Jessica, your news presenter. Plastic pollution has been a global problem for decades now and is only worsening over time. According to the Ocean Literacy Portal, around 80% of the plastic waste contributes to ocean pollution. And by 2050, the amount of plastic will outweigh all the fishes in the sea. As a result, 1 in every 3 fish contains microplastic. Furthermore, the plastic that pollutes our land will break down into toxic microplastics that contaminate soil, waterways, and eventually our food chain. While you may think that finding plastic in our food is not that serious, it can cause serious issues for us. For example, it can cause damage to organs such as our skin and eyes. It also causes cancer and decreases our immunity, and other kinds of harmful effects as shown here. Do you know that we approximately eat 1 credit card each week? Isn't that horrifying? So here comes the important question. How can we prevent plastic pollution? We can prevent plastic pollution by degrading them. One of the key technologies to solve this problem is enzymatic degradation of plastic. To explain more about this, we have invited Candy, one of the researchers in the area. Welcome, Candy.
Thank you for inviting me.
You're welcome. Please do tell us more about this technology. Can we really use enzymes to degrade plastic as the name suggests?
Yes, so we can actually use enzyme to degrade these plastics.
Oh, interesting. What kind of enzymes?
The enzymes belong to the hydrolyzed family, such as lipase, lactases, kinases, esterases. So one thing to highlight about these enzymes, like they have to work in the presence of water, which is why they are also called the hydrolytic enzyme.
How do you obtain these enzymes?
We isolated them from algae, actinomycetes, bacteria, and fungi which have degraded plastic materials. For instance, the esterase enzyme here is isolated from the yeast, Pseudoxyma, and Patica.
How does this degradation process work?
Basically there are two steps. The first step is called the hydrophobic reactions, where the enzyme needs to stick onto the plastic surface. But we all know that plastics are hydrophobic, which means that nothing can stick itself onto its surface, which means that so what the enzymes will do is like they have their own hydrophobic regions. So they will stick that hydrophobic regions into the hydrophobic surface of the plastics. Now the enzyme have already stick itself onto the plastic surface. So the second step, the enzyme will actually use its own active site with the help of water to clean or break apart the larger polymer molecules into smaller molecules that can be used as a carbon source for microorganisms. So in a simple way, the hydrolyzed enzymes attach and then collaborate with water to break apart and then degrade the plastics.
Oh, what an interesting process. Thank you, Candy, for coming down here to explain this technology to us. Let's take a look at what chemical engineering students from Temasek Poly have to say about this technology. What do you think are the benefits of enzymatic degradation?
I think it will benefit the environment because enzyme can break down the plastic like PET into the reusable monomers, and which significantly reduce the breakdown of plastic since it usually takes hundreds of years to decompose. Also, it can avoid the harmful byproducts that result from banning some plastics and also the toxic chemicals for recycling. So it's a cleaner and more sustainable alternative. It will be energy efficient. Enzymatic process occur at room temperature and neutral pH. So unlike traditional recycling methods, it doesn't require high heat or chemicals. This makes it much less energy intensive, which contribute to the reducing of overall environmental footprints of plastic waste management. It will help maintain a circular economy. Enzymatic degradations help create a circular economy by breaking the plastic down into their original monomers, which we can reuse it again to create new plastics. This reduces our reliance on the virgin materials and minimize the waste, and it will allow us to recycle plastic more effectively, thus supporting the principle of a closed-loop system where products are continually reused and recycled.
What do you think are the risks of enzymatic degradation?
I think firstly, detecting and isolating microbes that can break down plastic is a slow process. Most microbes are naturally adapted to degrade organic matters like plants and animals residue, not synthetic polymers. Plastics are relatively recent invention and only a small subset of microbes have evolved mechanisms to break them down. Identifying these microbes requires sifting through various microbial populations in diverse environments such as soil, compost or marine ecosystems where they might exist in low abundance. Enzymatic degradation is limited to specific plastic like PET, PLA or PA, plastic that contain carbonyl groups. Unfortunately, that does not include widely used plastic like PE or PP. PETAs, for instance, work only on PET. Mixed or multi-layers plastic further complicate the process because they require multiple enzymes to degrade different layers. One potential byproduct of plastic degradation is methane. Methane is responsible for about 25% of human-induced warming we are experiencing today. Although small amounts of methane can be captured and used as energy source, high levels of methane contribute significantly to climate change, exacerbating issues like extreme weather, sea level rise, or ecosystem disruption. Also, in high concentration, it displaces oxygen, which can lead to respiratory issues and cognitive impairments.